All right, welcome back. So one last reaction to look at, and that is a zero order reaction. So let's say we've got A going to products, and the rate is equal to K times by A to the zero, which is really just K times by 1. So the concentration of A has no effect on the rate whatsoever. So that seems kind of weird. We can go ahead and we can write down the rate. So the rate would be the change in concentration of A with time, where we flip the sign because it's a reactant, and it's equal to K. So we can do a little bit of calculus here, right? So if you've taken calculus, this is kind of a little bit of fun here. So we are essentially just integrating, and that's why they're called integrated rate laws. But I like to think of them as concentration versus time equations. And when we do that, we get the concentration of A at time t is equal to minus K times the time plus the original concentration. So we can go ahead and we can say that this actually looks like the equation for a straight line. If you went ahead and wrote y equals mx plus b, and you plotted the concentration on the y-axis and the time on the x-axis, then you would find the y-intercept would be the original concentration, and the slope would be the negative of the rate constant. So we'll go ahead and plot that. So that's your concentration, and that's your time. So it is a straight line that is going down. So that kind of makes sense because the concentration is being used up. And the slope itself is equal to the reverse of the rate constant, only if it's zero order. So we can use that as a test, right? So if it's first order or second order, then the concentration curves are going to go down much more quickly than if it's zero order. So this is kind of one of those weird things, right? You might think, well, surely the concentration of the reactant must affect the rate of the reaction. But it turns out under some situations, it does not at all. And this is often where you've got, say, an enzyme catalyzing a reaction. And it turns out that you've only got so much enzyme in your body, so it doesn't really matter how much substrate or how much reactant you have. It's always waiting on the enzyme to kind of free up and give it up an active site, a place to react, and then go ahead and convert it to product. And you might think about, say, going to a grocery store with only one cashier in line. You might think the more people waiting to check out, the faster the process should be. But of course, if you've only got one cashier, you're going through that cashier at a fixed rate. It doesn't really matter how many people are in the line. If they just leave one cashier open, you get that fixed kind of rate going through that is completely unchanging with time. So that would be an example of a zero order reaction.